Welcome back to our class on machine translation. So now armed with tools from deep learning, let me revisit an initial model that we discussed before in the terms of statistical methods, namely language models. So we're not going to make it all the way today to translation models, but we make it about 80–90% there. Moving from these language models to translation models is going to turn out to be a surprisingly small steps. So here is how we previously approached the problem of language models. So we built this idea of an n-gram Backoff language model. So language modeling is a task of given a string of words, what is the probability of these string of words just happening to appear in the world? Think about it, opening a book at a random page and looking at a random sentence. How likely is that sentence to occur? So um, the way we solve this is to predict one word at a time. So this was first using the chain rule and then also introducing the Markov assumption, where we say we only care about a limited history. This made this whole thing much more practical. So we can, for instance, if you have a 5-gram language model, collect counts over 5 grams. Sometimes we have enough statistics to estimate that, otherwise we back off to smaller windows. So these are n-gram language models, and they're very powerful, and they've survived for decades. They have one drawback, obviously. They're very harsh, limit on the history of 5 words, and sometimes even less. So we went through various refinements. There's a whole family of Backoff schemes. Contouring, Witten-Bell, Nathan-Nye, modified Nathan-Nye, interpolated Nathan-Nye. There are also ideas about, well, what if I haven't seen the biogram, but I've seen this word in the context of another word, but that was once removed. There's also the idea of class-based models, of saying, let's have models over the part of speech tag sequences. So we've never seen this noun before, but we know it's a noun. So yes, this is a natural context for a noun. So what we're all wrestling here with is we want to use as much relevant evidence as possible, but we don't really have a good way of pooling evidence between words. So here's now how we're going to approach this problem as a neural task. So basically this is just the n-gram language model translated into a feed-forward neural network. So it's really just like the XOR example, except the inputs here are not 2 bits. The inputs now here are 4 words. These are the 4 words of the history. How do we represent them? Let's get back to that in a second. But we have these input words. We're going to feed that into a hidden layer, and then we make a prediction into the output. And we want to predict the probability distribution, and we're going to use softmax, so that hints already a little bit how we represent words. So basically, if we have a vocabulary of 50,000 words, we're going to have a vector with 50,000 values that we predict at this point, and how much each element gets after the softmax, how big that value is, indicates the probability of that word being chosen. So the most likely word, the one with the highest value in that vector, will be picked by the model. So this is the idea here with representing words. So we represent words with a one-hot vector. So this is the idea of having, here 50,000 word vocabulary. That's a vector of the size 50,000. That's a large vector. And it's actually in none of the existing neural models practical to actually have a vector over the entire vocabulary. So there are various shortcuts that are being taken. I'm hinting at a few here. We're going to revisit the idea of how to represent words for neural machine translation in some future lecture. So here are some quick remedies. Let's just look at the 20,000 most frequent words and the rest are other. For language modeling purposes, that's probably enough because anything that's not one of the 20,000 most frequent words is just a rare word, and then predicting it or not predicting it doesn't matter so much. It's rather rare. 99%, 0.99% of the time, you're not going to encounter such a word. Another idea is to kind of have the idea of let's just break things up into classes. So if we have 10,000 words, let's say, and we have 100 classes, and each class has 100 words, then each word is identified by a class ID and a word ID, and the 100 classes, the 100 words in the classes. Okay, so we only need a 200-dimensional vector. So that actually saves quite a lot of time. What kind of classes could you use for these two hot representations? So there are two, one for the class, one for the word. You could do wordlet classes, brown clusters, frequency binning, all kinds of things have been worked, and they all seem to work equally well. Okay, let's move to the idea of word embeddings. So this is our model, and we're going to add now another hidden layer, which is the embedding layer. So this here is our new thing that we just added. And why do we do that? So the idea is to first map each word into a lower dimensional, real valued space. And you can have then a shared weight matrix E that you apply to each word. So it doesn't matter if it's the forward prior, two-word prior, or the preceding word. You're always going to use the same embedding matrix to first have a word-specific embedding. So this really means that each word, no matter where it occurs, has a representation that is fixed. So why are we doing this? One big argument is obviously deeper networks are nice, and then maybe having unique word representations based on independent of where the words occur is probably also going to be helpful. So that seems to be a reasonable processing step. It's actually quite powerful. What I just described here is the neural language model proposed by Bengio in 2003. Some more details about this. So input to embedding, there is no activation function because it's really just a lookup table. Remember, you map from a one hot vector and to an embedding. That just means really that that weight matrix is just a big lookup table. Row number one is associated with word number one, row number two is associated with word number two, and so on. Then from the embedding to the hidden layer, we have the 10H. That's just a slight different variant of the sigmoid function. And then from the hidden to the output, we use softmax because we want to predict the probability distribution. So we can train this by looping through the entire corpus. So this is really one of the most straightforward applications of taking an n-gram language model and translating it into the world of neural prediction. Why did it take so long until 2003 for someone to come up with the idea? Well, the idea is not really the key here. The key is to have the processing power to actually build these things. And that's really just possible since the last 10, 15 years. So here is just kind of draw attention once more to this idea of word embeddings. If you're taking a word, which here we kind of indicated by a one hot vector, all the other values are zero, and we're going to map that to an embedding. That's really just a hidden layer. However, we can actually look at these word embeddings, and they turn out to be very, very powerful tools. So one thing that falls out of this, if there are two words that occur in similar contexts, they receive similar embeddings. So this is very close to the idea of distributional semantics. Here's a visualization of taking these highly dimensional 300, 500,000 vector embeddings for words and just display them in 2 dimensions. And what you see there, if you blow it up, it's going to be a bit more clearer, is that words that have similar meaning actually get very similar embeddings. So these are all words here: playing, scoring, winning, losing, that are associated with sports or any kind of competitive game. Down here you have growing, developing, that means something very similar. Up here you have a lot of words from the media space. So you have a lot of related words. So this created a lot of excitement in the world of natural language processing. So we're now here citing a paper from 2013 where these two pictures are taken from. Note, this is 10 years after the original proposal of Bengio's neural language model, so it took a while to actually make this practically work. But once it worked, people got excited about the word embeddings that were created by this process. So various claims were made in this paper. For instance, these are all words here where you have man, woman. The only difference is the gender, otherwise they're kind of the same concept. Uncle, aunt, the only difference between uncle and aunt is the aunt is female and uncle is male. King and queen, also a similar relationship. There are great ideas about doing a kind of vector arithmetic with these word embeddings, and it seems to work to some way. Maybe there's just a unique pluralization vector you can learn. So this is actually turning it to female. Okay, there are various other semantic regularities. For instance, how it's a relationship of clothing to shirt and dish to bowl. Do they also have similar vector relationships, and so on? And people have also evaluated similarity with human judgment and compared it against the similarity of vectors in this vector space. Okay, back to our quest of building neural language models. So we already have one that we presented, which is really just taking the n-gram language model that we know from statistical natural language models and converted that idea into a neural space. Here's now a better idea, which are recurrent neural networks. So we still predict one word at a time. However, we create a process that takes a prior word into account, maps it into embedding, has then maybe also the same kind of hidden layer 10H and softmax to make predictions. But we're also going to draw on some kind of prior state. So what is that doing? What is it doing here? Well, it should be more clear if we actually make the next word prediction. So this is our first word prediction. And now we're going to do the next word prediction. So whatever word we actually predicted here, so here we predicted word 2. Now when we make the next prediction, we feed that in here, or if we know the truth, we actually put in the real word 2 here. And then we make a prediction here as well. So there's a couple of things to note about it. So the prediction we make here depends if we kind of draw through these graphs. So this prediction depends obviously on word 2, but it also depends on word 1. So we're making a prediction based on those two words. But instead of having a complicated models with 2 inputs, the way we do it is by just copying over this hidden state that we computed there. So this was not really the final prediction. This is kind of the hidden state. It is not the prediction is a softmax, but we copy that over to make the next prediction. And we can keep going with that. So if we now predict the fourth word, after inputting word number 1 and word number 2 and word number 3, we're predicting now the fourth word, we kind of repeat this process. So this, the parameters involved in each of these predictions are the same, but the inputs change. First of all, the actual input word changed, and what that hidden state is also changed. So how do we train this? So if we just make the first prediction, this still is kind of in the space of how we thought about backpropagation before. So this is just computation graph underlying all this, and we're just gonna feed back the error into updates. So we can do this for another word too. We can do this for the second word, and then also feed up updates for another word. So for instance, at this point, we have to feed back into how to update the embedding on the one hand, but also how to update the relationship of hidden states to each other. We don't have actually a connection to the previous word, so we don't really connect this back up to word number one. So how can we avoid that? The way to avoid that is backpropagation through time. So instead of checking at each prediction and tracing it back to its inputs, we're now going to unfold the entire computation graph. So far we thought about computation graphs as some fixed thing. There's a neural network architecture, it has a computation graph. Now the size of the computation graph actually depends on the input. We're dealing with sequences, they can have any length. So these computation graphs, when we actually unroll them, become very, very large, and they're definitely dynamic in size. So this requires clearly a more powerful toolkits to support these kind of dynamically created computation graphs, and this was also a key thing in the development of more advanced toolkits. But once we have it unrolled, let's just say this is a very simple example where we just have a four-word sequence. We predict the second word, the third word, and the fourth word. And each of them gives us a cost. We kind of sum up over all these costs. So we can also add them up together, and then that feeds up backpropagation through all these things. So backpropagation through time, initially it created very large computation graphs, and initially that was a big concern computationally. So maybe you don't have to do this for the entire, for instance, 20, 30, 40 word sentence. Let's just do backpropagation. Let's just enroll it for 5 words at a time. That seemed to be sufficient. But more recently, these things actually really get unfolded over the entire sentence. Another one is to update in mini batches where we process 10 to 20 training examples at a time, for instance, and then update backwards through all these examples. Okay. One more refinement on the recurrent neural networks that we introduced here are called long short-term memory networks. These get mathematically a little bit convoluted, so it's not that important to fully understand all the intricacies. However, they do address some key problems with recurrent neural networks, and similar ideas also gonna play a role when we, in some future lectures, move to more complex architectures. So one key problem is this problem of vanishing gradients. So the error is propagated to previous steps. And the updates consider the predictions at that time step and the impact on future time steps. And we're multiplying up a lot of numbers. So there's a concern that if the weights are set in a certain way, all these numbers kind of tend towards zero. Once you multiply numbers below one over and over again, they become towards zero. So and kind of really prior, if you kind of move up to earlier and earlier stages in computation graphs, you actually have gradients that are around zero, so you don't really have any updates. There is a problem with this architecture is that the hidden layer plays a double duty. First of all, it's the memory of the network. So theoretically, it encodes all the previous words that were counted. But then also it's a continuous space representation that is used to predict output words. And sometimes only recent context is really important. So after much economic progress over the years, the country has. So to predicting the word has, well, you really just need country for that. That has is a word that can follow country. It doesn't really matter what all these other words are. They're not going to have much influence on the decision. If there would be different words, you still probably have the same probability to make the decision that the word has follows. But sometimes much earlier context is important. So if you look at this example, the country which has made much economic progress over the years still has. So now the word that is so important to predict that this has, for instance, that is a singular verb, not plural verb, is influenced by country, which is a long time away. So this information is very relevant, and any model that makes a prediction of has here has to be aware that has to have stored away somewhere the information that the subject of the sentence is singular, and that is something that will then can be used to predict the right inflection of the verb. So the long short-term memory is a somewhat elaborate design, but it's not really very complicated to use. So the very basic building block is called the LSTM cell. It's similar to a node in a hidden layer. So we basically still have the same architecture. We're just going to swap out that hidden layer node with something that is a bit more complicated. One thing that it does, it has an explicit memory state. So the hidden layer always had a state. The hidden layer is a state. In our examples, the hidden layer was a vector that functions both as a memory state and as the key to make a prediction, word predictions. Now we actually separate these two roles. And the way we separate these roles, LSTM takes a lot of ideas or metaphorical expressions from how you actually build very basic circuitry. This idea of gates that flag if some information flows from A to B is used in gates. Really think about AND gate and OR gates and all that. That's where this word gate here comes from. Here, however, obviously we have probabilistic gates, so they're never really 0 and they're never really 1, but they are, tend to be closer to 0 and tend to be closer to 1. So we have gates for how information gets transferred. Here's now the picture that represents all the computations that are going on. Okay, so first of all, this is kind of the hidden state. Previously, it was just a single hidden state, one vector, and had like just basically a vector with values. Now let's see what happens to each of the values in the vector. So we take there's a memory, a value associated with it. This gets passed in and through a forget gate. So this basically controls how much that memory gets retained or gets deleted. So in some circumstances, memory gets deleted. In some circumstances, gets retained. So that has an impact on the new memory. The new memory also obviously is impacted by the input that just came in. So this is the preceding layer going in to update the memory. So this is now the memory. From that, we make an output prediction. So the output gate. So only some of the memory is relevant for output predictions, and some of the memory is just there to kind of retain across states. And that kind of is then the hidden value. So literally the calculations here are input gets scaled by a gate and a memory gets scaled by gate, for instance, to update the memory, and here is the output gate that gets scaled by the output gate. So you need to have these gate values somehow. And then we have to compute the hidden node value that is passed to the next layer here. That's just the activation function that is applied over this output value. Okay, down here you just kind of have the whole calculation kind of spelled out in terms of just the weights that go into these calculations. So for instance, here, the input that is being computed is based on, yeah, the actual input vector that goes in here. So we're looping here over all the elements of the vector. Each gets multiplied with a weight. So this is a typical matrix multiplication of a vector with a weight matrix. And here we have then the same thing for the hidden node. So the previous hidden state gets also weighted with a weight matrix. And based on the size of the hidden state, we're looping over that. And finally, there's some activation function G that's applied to it. So these gates seem to be very important. They seem to be doing really smart things, like in this case, memory is important or memory is not important for these particular values in the element. These particular elements in the vector memory should be retained, and over there memory should just be deleted. So how do we get these gate values? Well, we're just gonna do another neural network layer for that. So we have basically this computation here of a gate based on a weight matrix of the various inputs that go into it, and we just throw in everything into it. So that's the node value of the previous layer. So that might be just kind of, in our example, the input to the hidden layer. Then the node value of the same layer at the previous time step. And we can also feed in the memory of the previous time step. So all that kind of goes into there. So that just becomes then a usual weight multiplication with these vectors and an activation function h. So how do we train these things? So this is just a more complicated computation graph. And we're going to do the same thing we do as we always do. So they're trained the same way as recurrent neural networks. So they have to have the same issue of how to deal with backpropagation over dynamically sized computation graphs. But we talked about this backpropagation through time. So this looks all at this point rather complicated. But keep in mind that these are just all mathematical operations that are all still based on matrix multiplications or differentiable activation functions. So we can compute gradients for them, and we can compute gradients with respect to all the parameters, and then it allows us to update the parameters, and we can update all the updates accordingly. So what's the point? So here's a nice illustration with a slightly different architecture, but that kind of illustrates how that you can use these kind of gates to indicate, to somewhat flag what kind of memory matters. So these are now for various languages. First two are German, and the last one is for Italian. When it makes word predictions, like here, the word up, what does it depend on? So what actually mattered the most to make this prediction? So yeah, the previous word seems to matter, but here a very, very long distance word seems to matter. And this is a relationship that's kind of like switch on the light. So yeah, switch blah, 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 blah on. Here, the word abhängen means to depend, but it's kind of split into two pieces and they're very far away in German. Here you have a verb, play, and here is the subject, a key role, play, and they play a key role with the ambitions. Here you have titolo, so title, that depends a lot on things like emperor and awarded. So you see kind of semantic relationships of words that are in the same semantic space. So you can look at this paper where they discuss a bit how actually these kind of gates help to illustrate the inner workings of these neural networks. Here is another interesting visualization of neural language models where we look at individual cells and see how they kind of change over time. So we're looking at individual elements in the hidden states vector and basically want to know, are there some elements that play a very particular role? And apparently there's here one element in the vector that basically predicts here when the line break should occur. So this is now a model over character sequences, but that also explicitly encodes a line break. And the longer the sentence gets, the longer you are in a particular row, the longer you haven't seen a line break, the probability of a line break occurring increases slowly. Here's another one interesting. So there's a quote here, and then one of the elements in the vector gets turned on, and then here it gets turned off. Here it gets turned on again. Here it gets turned off. So it is somewhat rare to find individual cells, so individual elements in the vector, to have such a stark and obvious role. Most of the time, the information is a bit more diffused across various elements. I have two more examples. One here is when you train a model over computer code, so opening parentheses and so on being flagged. But down here you see a cell that really has no obvious role. It seems to be going up and down all over the place, and it's not quite clear what it actually does. So a large portion of cells are not easily interpretable. Let me finish up with just kind of mentioning gated recurrent unit. So this is a slightly simplified version of the long short-term memory cells that used to be quite popular in the design of neural language models and neural translation models. So this has a slightly different design that only has two gates, a reset gate and an update gate. So that makes it a little bit easier. So you have the hidden state getting passed through here. So here's the math for it. So you have the input going into the cell. You have the previous state, and you also have a bias term, and so the update gets influenced by those two, and the reset gets influenced by those two. So the gates are influenced by kind of all the relevant information. Here is the kind of intermediate processing here of combining the input with the prior state, and then here's the computation of the next state. Okay, another variation of this theme of recurrent neural networks is to move towards deeper models. So these are the models. So they get quite long in terms of neural network design. We're far away from XOR, so there seem to be fairly a lot of processing going on. But the reason why there's a lot of processing going on has to do with that we process long sequences. The connection from an input word or the embedding of an input word to an actual prediction is still very, very shallow. There's only one hidden layer. So why don't we have more hidden layers? And there's various ways you could do this. This is one here. In any case, you're gonna go from an input where it's embedding to a prediction now over various hidden layers. So that doesn't change. But then the question is, how are the hidden layers connected to each other? So they could be horizontally connected. This is called a deeply stacked deep model. And or they can just basically go through this entire processing chain and then move on to the next. We're passing the state of the last layer in this stack to the first layer in the stack when processing the next word. And there's also mixes of these architectures. So this is it for today. And finally, we're going to go back to translation in the next lecture. And as I promised, it's actually going to be a very, very quick transition from language models to translation models. We don't have to do all that much to finally get to translation models. So wait for that in the next lecture.